Hey, how are you? Yay. Get the homework done?
I still haven't had anything for that last one.
I just messed with it and it seemed to work out, so.
Yeah.
Oh, I figured out this, this I did a bunch of replacing like gamma mu with two 8 mu minus, so these ones became this, and expand it out and then do that again, and if you do it the right way it works out.
Yeah.
So I think it worked out. I wasn't really confident.
Good morning, everyone.
Good morning.
All right, so we're going to continue quantizing the direct field and now looking at interactions. We saw at least last time how we got the propagator out. So now let's start using the propagator. So now we'll look at real Yukawa theory. So real in the sense of how Yukawa actually wrote it second, whenever it was, many decades ago. So it's real because now we have fermions. So the way he wrote it was as an interaction between fermions through the exchange of a scalar. So now we can go back and look at the same scattering process we did before, but basically, so the ingredients for this theory are a Dirac fermion psi with Sn and a real scalar pi with mass, we'll call it mu. Well, eventually we'll actually look at other types of interactions we could write. But here we'll just guess the simplest one. Right, it could be, by the way, right, that this theory is the most boring possibility, and that they don't interact at all. So even if that's the case, we know what ingredients to write down, right? So if it's a real dynamical field, that means it's got to have some kinetic term. I have to have a kinetic term for each of these, and I'm told that they both have a mass, so each of them has to have a mass term also. So I have my normal kinetic term for scalar, and minus 1/2 u squared phi squared. So that's the part taking into account the mass of the field. Then I have the Dirac part of the Lagrangian. So psi bar I gamma mu partial mu minus little m for his mass. So right, we could just have this possibility. It would just be two fields, one a scalar, one a fermion, and nothing happens, right? If I start sending psi's at phi's, or doing any sort of dynamics, right, nothing would happen. Things only start to get interesting if I add in a term. I'll call it coupling lambda. And it'll be very similar to what we had when we looked at our purely scalar Yukawa theory, right? Before we had a phi side dagger side, where psi and psi dagger were complex scalars, and now they're complex fermions, or Dirac fermions. And everything's controlled by this coupling lambda. So this is just like the important thing is that this is now at least an actual interaction in nature. So terms like this appear in the standard model describing the interaction between the Higgs scalar and fermions. So Higgs and core fields have interactions like this. Higgs and lepton fields have interactions like that too. And you might know the story that there's some potential for the Higgs field so that this gets a vacuum expectation value and generates a mass. That's beyond what we're going to do now. We're going to look at the dynamics of this, but so this is just like the Higgs fermion couple from the standard model. But for Yukawa, he was interested in this as a description of nuclear forces. So he wanted to understand how through meson exchange, like pions, which are scalars, how you can describe nuclear forces among fermions like protons and neutrons. So that was why it bears his name. Started studying this a while ago. So right, let's also remind ourselves just of dimensions, because this is another difference between real Yukawa theory and the Yukawa theory we studied before, is that the interaction is different. It's of a different mass dimension. So let's remember again too, how would you figure out mass dimensions of things? If you forgot everything, we know at least Lagrangian has to have mass dimension 4, because when I integrate over all space-time, it gives me an action. And an action has units of h bar, which are unitless for us. So he has to have mass dimensions 4. Spatial derivatives, 1 over space, or 1 over time. 1 over time is mass. Right? So I have mass squared, so I have 2 derivatives. So that means phi has to have units of mass, right? Let's just recapitulate everything. stuff. So the mass dimensions of the Lagrangian are 4, which means 5 has to have units of 1, because this is 1. And that means mass units of mu are what you'd expect. It's 1. It's a mass. And what about psi, though? I think we talked about it, but psi has funny units of mass.
3 halves.
Again, this thing has to be units 4. This is 1. So I need a psi, I need psi bar psi needs to be 3, right? And psi and psi bar have the same mass unit, so psi has to have units of 3 halves, which is kind of funny. But that means then this term, which has 2 psi's, so it gives me 3 plus 1, so that's 4, right? So lambda is dimensional. So lambda, remember, right, if these guys were scalars, it'd be 1, 2, 3. And then lambda would have units of mass. That was what we call a relevant interaction in that case. Now, because it's mass dimension 0, it's called marginal. Which roughly means it's relevant. It's sort of energy independent. Its effects are independent with energy. They grow very strongly with energy for irrelevant operators, and have opposite energy behavior for the relevant operators, like the scalar version of the Yukawa theory. So, okay, so now we want to go back to dynamics and actually calculate something, see how all of this plays out. Right? We could go back and look at many of the same processes we looked at. We could start to go back and look at same processes, which will have different amplitudes. We can look at psi scattering. Now these are, I have to think of this as particle-particle scattering. We could look at psi bar scattering, or psi bar psi annihilation. All of it's going to be different. The same basic processes can happen as happened in the fake Yukawa theory that was all based on scalars. Right, I can write down these same basic processes that can happen, but now the calculation is going to be different because now I have fermions. So, and also just like before, we'll suffer a little bit before we use the Feynman diagram method. So I'm not going to do a full, quick theorem calculation with fermions because it's even worse, but we'll start it so you can see the ingredients and also see why no one does it like this anymore. Okay, any questions about real Yukawa theory? So we'll do it the hard way first, and also not even do it fully because I'm not going to go through all the steps. We're taking more than, probably take 2 whole classes or something to do it properly. So we're going to look at psi scattering. And first, the hard way. Okay, so we're not going to use Feynman diagrams, but I can't help but draw something. I'll just draw it as a blob. So I have some incoming fermions, which now, in addition to having to worry about how their momenta come in, I also have to worry about everyone's spin. So that's step number 1 that's sort of going to be an additional complication. So I have fermion with momentum p coming in with spin s. and I have other fermion with momentum q coming in with spin r. They scatter into some new states, ps prime, sorry, p prime and s prime, p prime and r prime. Is this notation okay with everyone? First thing is just momentum, the second letter is the spin. So, in other words, I could write down initial and final states because I know how to create them out of the vacuum, right? I had my annihilation, or sorry, my creation operators for that. So, my initial state is going to have right normalization, all that's fine. I've got a P and a Q with energy. And I create those guys by acting on the vacuum, right? That's how I created it out of nothing. But for shorthand, right, I can just carry around the notation that this is a P comma S semicolon a Q comma R. So that's for the initial state, and the final state is the same sort of thing, but everyone has a prime. And right, also since we're ultimately going to sandwich this, right, to find the amplitude, what do? We sandwich F and I with the S matrix. So I'll have to take the adjoint of that. So just remember that in terms of annihilation and creation operators, when I make the bra of this F state, he's going to be written with annihilation rather than creation operators. So that's that same energy coefficient, but now it'll be with 0 and annihilation operators. Okay, so it's been a while, right, since we calculated something, one of these matrix elements. So we have to remember, how do we do it? What we want to do is we want to calculate this S minus 1 sandwich between initial and final states to order lambda squared. So we'll have to have at least 2 insertions to find psi scattering. 2 insertions of the Hamiltonian. So right, what were all the steps of what this thing meant? Do you remember? What is the S matrix? Or how do we? So we're not going to jump to the Feynman method yet, but originally, right, what we defined it as, so we had our old-fashioned propagator, our U propagator, the analogous thing from non-relativistic quantum mechanics, the time evolution operator, we should really call it, I guess. That's basically how we defined what the S matrix was, right? So this is what we want to do. Let me just remind us about what all of this means. So we basically defined S, and this is really, we defined this matrix element as being a thing, if I know what's going on at plus and minus infinity, of what happens if I just insert this time evolution operator, right? So it's what takes me from t minus to t plus, where now I imagine I know everything out of the infinite past and I want to evolve it into the infinite future. And the reason we have to do that again, right, is because ultimately we want to work in the limit that all of our states are free theory eigenstates, right? So ultimately, I don't know how to deal with interactions unless it's sort of a small deviation from the free theory. And I know what the eigenstates of the free theory are. They're momentum eigenstates. So, you know, as long as at infinite past and infinite future I stay as momentum eigenstates, I know what's going on, and I can think of this as just some small, you know, it's at least not changing my eigenstates. So that's basically why this works. And then the other big ingredient we use is we only know how to deal with the time evolution operator using Dyson's formula, and also using it perturbatively. Dyson's formula, this is all in the recall category of things. That time evolution operator from Dyson's formula it's the time-ordered exponential of minus I of the integral over the interaction picture Hamiltonian. And this is the real Hamiltonian, not the Hamiltonian density like we usually deal with. So for us, right, the interaction part is really a lambda d3x of the term in the Lagrange, the thing that was over here that I erased, which is phi psi r. So this is all sort of stuff that's somewhere back in our memories. And the last important ingredient for how we actually did these calculations, you can see why we don't do it anymore. There's a lot of baggage. We used Wick's theorem, which told us how to convert a time ordering into a normal ordering, plus contractions. So the other important thing we had to use was what happens if I have some product, some time-ordered product of fields, which I'll get because I'm always going to be doing some finite Taylor series expansion of the exponential, right? Here I'll have to do it to order, just a second order. So I'll always have some product of fields, and Wick's theorem says I can turn a time ordering into a normal ordering. I have these double dots, where double dots mean, right, I move all of my creation operators to the left. I do that plus normal ordering of all possible contractions. The only thing that makes this actually usable is that typically, rather than all possible contractions, it's only one that matters. And it's like that for us too. So, okay, so these are the big, important pieces of machinery that let you do the calculation, and which are important to remember because they're also how you can derive the time intervals if you want to go that route. But that's a lot of work too, and beyond what we're going to have time to do in class. So, but this is what we want to do, right? So we can write down, this is all up in the clouds of our memory. So let's write down now how we would do it in our theory, at least the first set of steps. So we have to do this to second order, so I'll have two insertions of this Hamiltonian. The other thing that we do, and that we did last time too, right, is since really, you know, the time evolution operator likes the time integral of the total Hamiltonian, right? So I may as well just combine this d3x with this dt to get a d4x, right? And moreover, I'm going to have to do that twice. I'll have two minus i's and two lambdas, so I'll keep those together. And then 1 over 2, because this is that exponential Taylor series. So first space-time integral and second space-time integral. Right? Each of these are for 1 power of that Hamiltonian. And time ordering of a very big mess of fields. So psi bar x1, psi x1, phi x1, and psi bar x2, psi x2, phi x2. And all of that is time work. And the thing that makes this much simpler is that we only need to worry about the possible contractions. And it's the same one actually we encountered in the fake Yukawa theory when we had all scalars. Only relevant contraction is one where I have all the fermion fields normal ordered. Two double dots and phi's are contracted. So remember, we already know what that object is. The way to sort of connect with Feynman diagrams is contractions are the internal fields. So ultimately, we're talking about psi-psi scattering. Ultimately, that comes about from the internal propagation of some exchange phi. So that's why we have the contraction only on the phi. So we have to insert this and act with it on I, on our initial state. Oh, I forgot actually. Sorry, this of course should be sandwiched between an F and an I. Yeah. This is S1I. So, right, I'll just write it down explicitly because we're going to actually ignore this part for a minute. We already know what this is. This is the Feynman propagator, or the scalar, 1 minus x. This is sort of the funny thing, we don't know what it is yet. So we'll insert our field expansion. You can always do this, just a matter of how much you want to tear your hair out over it. But you can always do that, right? You can always figure out the right contraction, then insert the field expansion, and then start moving things around. And we'll do that just a little bit so you get an idea. So, insert the field expansion, which I'll just write down so we have in front of us. This is not something new. We expand the field, our normal stuff, normal integral in a Lorentz invariant way, and annihilation operators that equal minus IPx and plus CP dagger V. So there's another important physical thing to keep in mind when you're doing this. I mean, you can also just blindly follow what happens when you start acting with this on the initial state. But I guess we didn't actually talk about it much because we didn't do too many cases where we had. Oh no, that's not. We did actually do basically the same thing when we were doing the fake scale, the fake Yukawa theory. But this guy, what does he do, right? He so we can see directly what he does. So he's going to destroy particles and create antiparticles. Whereas side dagger does the opposite. Right? Side dagger would destroy antiparticles. I'm just saying in words what each of these two terms does. So for that reason, when I just look at, say, this expansion, I can basically ignore everything having to do with the C's. Antiparticles have no role here. Right? Because I'm just doing particle-particle scattering, right? Just side-side, no side bars. And there's just exchange over phi. So I'm going to ignore all C's. If I didn't, I'd have to follow around some C's, but eventually I'd see either they annihilate on the vacuum or they produce something that's orthogonal to the state in the final state, right? Because if I'm producing antiparticles, that has no overlap with my final state. So that's 0, 2. So anyway, you could do it either way, but it's similar to just think about what these guys actually do. But you can just ignore anything having to do with the C's. And we can look at how, when I have this normal ordering of fermion states, when I act with that on my initial state, what do I get? And I'm not going to do everything. I'll get a flavor at least of how to do it. It might be helpful on future homework. We're going to look at how that thing, what happens when that hits our initial state, which is proportional to just 2 creation operators times a vector. So in particular, we said that it was create a P momentum spin S and a Q momentum spin R. This is basically the first part of what's appearing here. Right now I use the Wick's theorem to replace the time ordering by the only relevant contraction, and it's just this propagator stuff is just along for the ride. But let's focus on what happens with these fields acting on the initial state, because they contain a bunch of B's. So when I do that, I'll write this down, but we don't need to worry about the details except the final part. Let me at first just expand and to do the field expansion on the size. The only way you can do this in a safe way is doing it very slowly, step by step, because if you wanted to insert all the field expansions all at once, you have four momenta integrals, right, to do. Because every time I do the insertion, I get 3 integrals. But still, too many integrals. So let's just do 2 of them for now. I'll call those new momenta associated with x1 and x2, I'll call them k1 and k2. So what I'll have is psi bar x1 now contracted with the spinner u sitting inside here. And also x2 bar will come with the spinner then. And there's some exponentials. E to the minus I k1 x1 minus I k2 x2. The important thing I want to focus on are all the B's that fall out. So I just have to worry about the B's, I said, and I'm just doing the field expansions of the sides, right? So now all of these those expansions come with a destruction operator, annihilation operator. And now they'll be stuck together with the initial state B's. All acting on 0. So let's first just focus on that thing. Because we'll see how secretly there's a lot of information encoded in those B's. They basically imply what I would like, right? Okay, what's the strategy? You know, it would be nice actually to have all the daggers on the other side. I always conserve daggers basically. I know, if I start out with 2, I'm going to end up with 2. But I'd like them to be over on the left-hand side so that any other possible terms will annihilate on the vacuum, and that'll start simplifying things. And that will be very helpful because basically what it will impose are a bunch of delta functions, a bunch of delta function relations between momenta, which will kill these momenta. Simplify things a lot. So this is the only part I'll spend a little time talking about, because otherwise we'll just sort of jump to the end, because it involves doing that. But let's focus on this term. This BK1, and I'll write it already in the right way I'm thinking about it as K2, N, the dagger, PS, PQR. So let's focus on that. So the reason for grouping them like this is, let me make things a little simpler. At first, just think about the manipulation of the 3 of them. So what's the core fact of the annihilation creation operators that we were belaboring? In comparison with scalars, they don't satisfy commutation, they satisfy anti-commutation. So that means, for example, what we want to use, let me even back up even more. The strategy is move B's to the right. And on the vacuum. So what that means is, right, we're going to have to start interchanging, guys. The only way we do that is by making use of the right commutation relation or anti-commutation. So what that means is we're going to use, for example, BP Q dagger is the reverse with a minus sign and coming with a delta function. BQ dagger BP. So he has spin indices too, but it's the same. So for the first one, so we have BK2 and BPS dagger, BQR dagger, acting on 0. So let me do the first interchange. So he stays the same. The first interchange means I'll write a delta function that looks funny because it's actually 2 delta functions. Right, really, maybe I should have written RS here. This means really a delta function on the spin, and also a Dirac delta function on the momentum, right? So I'm going to use that notation just to simplify writing a million delta functions, because there are enough delta functions. So I would get a delta function, and now they have the flipped order with a minus sign. BPX dagger, BK2N, and he's just along for the ride for now. So first of all, right, we have some success, right? Now this guy is one step closer to the vacuum. Right, so what is this? I guess I can just write it out as being delta K2P NS with a BQR dagger minus BP S dagger, BK2N, and BQR dagger, all acting on 0. Yes. So then I need to do this again, right? We can do the same thing. So let me pull this over. So I would get this same term is still there, delta K2P and S BQR dagger minus BPS dagger. And now in parentheses, now I have delta K2Q and R and minus BQR dagger BK2N. Right? So they just flipped the order of it. Oh yeah. And, yeah, nicely. That term I can forget about. Right? So this is 0 because this will first hit on the vacuum, and so that term just vanishes. So this is simplified quite a bit actually. So now instead, what I have are just two delta functions and one creation operator. One delta function and one creation operator per term. All that still acting on 0. So remember, this was only 3 of them. So if I act now with the final destruction operator, I just have to do this one more time to flip. So you could see doing it one final time gives you just that you have two terms that have a product of delta functions. So all you have to do is do those steps 1,000 more times, and then you'll have the final result. So, right, this guy, this is ultimately what we care about. K1, and acting on those 3, B, K2N, B, PS dagger, QR dagger, all on 0. So all I need to do is have him act here and flip, right? And so we can do it sort of in our head almost now that, right? Although whenever I flip, I get 2 terms that appear out of one of those terms is 0 because now, thankfully, the destruction operator is to the right and kills the vacuum. So the process of moving him past this guy will just impose that delta function, right? So in other words, this will be automatically, first delta function comes along to the right, and the next one for that term will be Q and K1 are the same, and N and R are the same, right? Does that make sense what I'm saying? Delta K2, Q is the same, that just comes along, and now by moving the K1 past the BP state, I get a delta function on K1P and also on their spins, which are S and M. So that's a big simplification. Now all the B's are gone, right? And on top of killing all the B's, now I have nice relationships between spins and momentum. So, right, the upshot of that. So one, successfully got rid of all the B's. And B daggers. We also killed the K1 and K2 integrals that I just erased, because now I know how the momenta have to be relabeled in terms of our initial momenta, right? K1 and K2 are some annoying momenta that I had to insert when I did my field expansion. Now I relate them to my initial or final momenta. well, maybe one of the most important things that it did also was this relative minus sign. So we'll see this more explicitly within the Feynman diagram calculation, but these two terms are the same except for one fermion changing places. So it automatically accounted for the relative minus sign from fermion exchange. All right, so let me just comment on what you could actually do. So backing up, what we did was we inserted the relevant contraction. We inserted that in between the final and initial states and started manipulating B's. And remember, we only did that so far for the field expansions of psi, not psi bar. So we still would need to do that basically one more time. We're just getting rid of all the B's and B bars in the final and initial state. Right, we also didn't deal with the final state. So I need to sandwich in the final state there. But all of that is very doable. At the end of the day, you'll be left with your scalar propagator, which comes from the contraction of the scalars, and a bunch of spinors that are contracted in the right way based on these delta. So we'll write down the final answer, and I'm strongly inclined to think about this as a homework problem, because you'll know the right answer from both what I'm about to write, but also from Feynman diagrams. So another bit of information maybe we forgot, but was that this is the S matrix element, which we're writing in terms of an amplitude, because we basically factor out the stuff that's common to all S matrix elements, this overall delta function on energy and momentum. That times some amplitude, which is specific to our case, right? The amplitude we find from doing this is fairly big mess, but not too bad. I think I have another marker. So we have U bar S prime. Oh, that's actually S prime. Contracted on the U. Bar R prime, Q prime, divided into U R Q. All that's divided by the scalar propagator with the right momenta, P prime minus P, minus mu squared. This is minus this big term, which is of the same form, bar S prime, P prime, dotted now into U R Q, U R prime, Q prime, dotted into U S P. And that all over Q prime minus P. And they have a relative minus sign, which is very important, but it's okay. Schematically, it looks complicated, but if you look back also at the same amplitude for side-side scattering for scalars, it's similar, except there's no spinners, of course. Otherwise, the structure is pretty similar. There's also different momentum combinations in the denominator because of ultimately coming from different diagrams that we'll talk about. Otherwise, it's not that different. There was a plus sign, though, crucially, too, in the scalar case, because scalars don't care about flipping, particle exchange.
What were those two channels called again?
So the T and U channel.
T and U. Okay.
Yeah. All right, so now we'll get the result automatically, basically, with Feynman diagrams. So let's talk about, if you spent a couple of weeks just doing these sorts of processes over and over again, you will discover Feynman rules, basically. You'll discover the right thing that's going on. But instead of having you suffer for many weeks like that, I'll just tell you what they are. There's secretly a lot of baggage that we're carrying around that could be nicely simplified with pretty pictures. So Feynman rules for fermions. So first, let's look at external fermions. So for example, if I have someone incoming, so my main vertex is something like this. So I'm always going to label arrows on fermions, where the arrow denotes the flow of charge, not momentum. But if I have an incoming fermion, not an anti-fermion, who has momentum p and spin r, that's just equal to a spinner with momentum r and p. So this is only for external lines. For internal lines, we use our propagator, just like we did for scalars. Internal lines give you a scalar, external ones give you the spinner. And if it's outgoing, so sorry, let me stress that that's incoming. So the flow of momentum is this way. If you had an outgoing fermion, that's equal to a U bar. This is P comma R guy coming in. So an incoming fermion and an outgoing fermion. There are very similar rules that we could guess, since we haven't used V for external anti-fermions. This is still incoming, but we draw the arrow the wrong direction because the arrow shows a flow of positive Noether charge, positive electric charge. This is incoming. So P is still going that way. And this gives me a V bar. On R. And for outgoing, keep going this way. Give me a V R. This makes sense so far. This is what we're writing. The next rule for vertices is easy because it's the same. The vertex rule is just, every time I have this. That comes with a minus I lambda. Minus I is coming from the expansion of the Dyson series, the Dyson formula. And the final one are what I deal with internal lines. Those are, we already know basically, but I'll just write them for completeness. So if we have a scalar, our scalar at a mass mu, and we keep around the I epsilon in case the right combination of momentum makes this diverge. But that doesn't always happen. And a fermion momentum has the same propagator almost, except a p slash minus m on the upstairs. So this is for scalar, this is for fermion. So, right, also some important things. So, arrows on fermions always flow consistently. We'll see what that means in practice, really. This is because of charge conservation. So in other words, by the way, the only way you can have arrows not flow consistently are theories that don't have charge conservation. So that would imply something like Majorana fermions. You can have arrows do weird things with Majorana fermions, but we don't need to worry about that. The other important thing is that so matrix indices are contracted at each vertex. We'll see how that plays out. Yeah, so you contract, for example, with external spinners, or sometimes other propagators if you have some really complicated diagram. Propagators. But that basically summarizes all the climbing rules we need now for this Yukawa theory. Right, we already encountered these two items before, scalar propagator way before, the fermion propagator just last class. The vertex is the same as it is in the other scalar version, purely scalar version of Yukawa theory. And the only really new rules are what do we do with incoming fermions or anti-fermions. And as you might expect, we could just nicely associate them with U's and V's. Okay, so now we can go back, following basically the same path we did for scalars. Instead of doing it the most laborious way with Wick's theorem, now we just have the raw ingredients to just draw a picture and write down the answer. Oh yeah, and we also, another pseudo rule is to include a -1 for particle interchange. You have to do that yourself. All right, is this all right to erase? So now we can do some examples. The first straightforward thing, we should go back to side-side scattering. See how we get it. So the first step in applying climbing rules is just draw the process, decide what order you're going to work at, and draw all the diagrams. So we'll do it at order lambda squared. Otherwise, we have loops and so on to worry about. So the diagrams are basically, they look the same as what we had before in the other theory. So one thing we could do is have, I have to draw arrows consistently. I just have two incoming fermions and two outgoing fermions. No anti-fermions anywhere. P has momentum P and spin S. P has momentum Q and spin R. P prime S prime and Q prime R prime. So I have that possibility. So right, this is also sometimes called T-channel. And the other possibility is that the labels basically are flipped. That this is still the, I just write my labels in the same spot always. But now it's a matter of which vertex is connecting which. Is the PS state connecting the P prime, or is the PS state connecting the Q prime or prime? Right? So each final state could be paired with either of the final states. So that's what the two diagrams take into account. And since this is coming from basically just fermion interchange, there should be a relevant minus sign between them. This is called U-channel, right? So we'll have a relative minus sign between diagrams from fermion interchange. Alright, so let's think about all the things we'll have to apply, right? So one, just thinking about, for the first diagram, say, we'll call that the amplitude associated. So let's call this guy number one, let's go number two. So the amplitude associated with that, so one thing I'll have to know is what's the momentum flowing here. So another sort of pseudo rule we didn't write here is momentum conservation has to always be satisfied at all vertices. So that means I know the momentum flowing here has to be what?
P prime minus P.
Yeah, P minus P prime or P prime minus P, one of those. So I know, let's just write actually, I guess. So momentum of the scalar is P minus P prime. And the way I'm going to contract things right, will be P comma S will be contracted with P prime S prime, and Q comma R will just go to Q prime R prime. So that means I can write down right away how to do it. Armed with the rules. So A1 will be minus I lambda squared. I have two of these vertices. And everything will be divided by this momentum, which is P minus P prime. Everything will be divided by that scalar propagator. So P minus P prime squared minus mu squared plus I epsilon. And now it's just a question of what's upstairs. And what was the Feynman rule? So for incoming states, the rule is the incoming fermion, I have a U. right? If it's an outgoing fermion, I have a U bar. And I contract them according to the rule of who's talking to who at each vertex, right? So that means I'll have a U contracting with a U bar with these labels, right? Does that make sense how we're doing it? We have U bar S prime, P prime, into USP. That puts square brackets to make sure we know those are the guys that are connected. And the same thing here, right? Again, I have an incoming fermion, so it's a U, and I have an outgoing fermion for the bar.
Yeah, the P prime.
What's that?
U bar
Oh,
S
yeah.
prime P prime.
Or
Oh,
the yeah, sorry, thanks. Here.
yeah.
Yeah. That's right. So, but that's it for the first diagram, right? The second diagram, because of the relative minus sign, I have to do that by hand to make sure he has a minus sign. Still have a minus side lambda squared for the same number of insertions. Now, what's the momentum here? So now it's P minus Q prime, right? The momentum flowing down there. So now this is diagram. P minus Q prime, right? So it at least tells me what the denominator is. Now I'll have a U associated with P and S contracting with the Q prime, right? So you can see already we're getting the right result. So S prime, P prime, that's going with a Q and an R. And R prime, Q prime is going with the P and an S. So this is a good example, right? Because literally just applying the rules gives you what we had before. Right? And also, right, we did maybe 1/4 of the work involved in doing it the Wick way. Right? I didn't want to go through all that in class, but get the same result. With just using the Feynman rules and diagrams. All right, are there any questions about this example?
I got a question.
Yeah.
So the reason we don't have an S channel in this example is because we need an anti-fermion in that case?
Yeah, that's right.
Okay.
Yep. Does that make sense to everyone else too? So S channel, so what is S channel, right? S channel is basically this sort of process, right? So because I don't have in my Lagrangian a psi-psi phi interaction, I have a psi-psi bar interaction. One of these has to be an antiparticle. The other way to see it too is from just thinking about it from a Feynman rule perspective, which is that fermion arrows always have to be consistent. So I couldn't do that. I need them to flow consistently through a vertex. I have to have this as being, and also this. Which means one of them is a particle and one of them is an antiparticle, right? So if we looked at psi-psi bar scattering, then we would also have S channel to worry about. Right? Does that make sense?
Yep, thank you.
Yeah. So, but the other thing too to worry about with psi-psi bar coming together is that they can also annihilate. So you also have to compare to, right, the other thing that can happen when a psi and a psi bar come together is they can also just produce phi's. So you have to compare the relative cross sections to see who wins, but both of those processes are possible, right? At least if it's kinematic enough. There's enough energy in the side-side bar collision to produce that. So actually, that's what we're going to look at next. We're going to look at this annihilation. It's a different, well, let's just draw it. Different set of findings. I mean, we're still using our same rules we just wrote down, but in a different way. S-channel things are more interesting usually too, because right then you can have the incoming momentum line up to be exactly the mass squared, and then you can have a big enhancement in the cross section. But we'll do one of those next time, I think. So another example we could look at is side-side bar. This is annihilation. I have no fermions in the end. So we also have to go to order lambda squared to see that happen. Higher order things can lead to it too, but that's, we need to minimally do that. So there the diagrams are similar. Other thing that will be new about this, right, is now I have an internal fermion. And now the propagator is from a fermion. So this is P and S. I just always use the same labels, right? That makes it easy. And we have that plus, again, the same sort of thing with everyone going skew, connecting different vertices. This is GS, this is G prime, S prime, Q prime, R prime, Q and R. So one, there are a few so key differences. Let's just think about things so we don't just blindly do what we did last time. But what are our key differences? So one, fermion propagates. Another is we have an antiparticle in the initial state. And the last one is that the final states are all bosons, so there's no relative minus sign difference. These add, right? You don't have any fermion statistics to worry about. So this means that they just add. No relative minus sign. All right, so again, in this case, the momentum flowing through that is P minus P prime. And here it's P minus Q prime. So let's write down what's the amplitude in the first case. Well, just like before, like we said, right, this is at order lambda squared. We have two insertions at the vertex. We always have that. That's where the similarities sort of end. So we have an incoming anti-fermion. So remember what the rule is for that? We had an incoming fermion, not an anti-fermion, then it's like a U.
V bar.
Anti-fermion, so we have a V bar. Yeah. So this would be V bar, R, Q. And the other big difference is because now there's no spin information basically, right? I wrote this as S prime, but there's no spin for the scalar, right? There's no spin information to soak up the contraction. he's to have an unpaired spinner, right? Only possibility is for him to come along. He gets sandwiched with the information from the Dirac propagator. So let me write that down, right? Because I have a p slash, which in this case is a p mu minus p prime mu with a Dirac gamma matrix plus m. Right, now my propagator is sort of playing a role. It's getting sandwiched in between the spinners. So I have this 4 by 4 matrix to worry about between the two spinners. And the denominator, it's the same by construction, except now it's an m instead of a mu. That's right. So this is, and just remember that this part here stuck in the middle, this is the fermion propagator. Right, this is a antiparticle. This is a incoming fermion. So now if we want to do the other term. So unlike before, right, there's a plus sign overall. There's no difference in overall sign between the two terms. I have the same sort of thing, but now the momentum is this p minus q. Prime. Mu plus m, and all over p minus q prime. Squared minus m squared. All right, any questions about this example? So next time what we're going to do is look at a few other processes, but also what we can do. So for next class we'll look at recovering the Yukawa potential. For psi-psi scattering and also psi-psi bar. Right, because if this is supposed to be sort of like almost QED, we know what the result is, at least the sign is for QED. Right, I mean, if I have particles, they should be repelling, but if I have particle-antiparticle, they should be attractive. We'll find that it's attractive in both cases, which again is from the fact that we have a scalar rather than a vector. So remember that funny theorem I guess we talked about at some point, that scalars are universally attractive. Tensors are too, it's only vectors that are funny that can have attractive interaction, or sorry, repulsive or attractive. So that's what we'll do next time. And then we'll basically, also going through a couple more examples, we'll basically be ready to look at gauge interactions of quantum electrodynamics. So we're on the path. And hopefully I'll assign a homework soon, probably before the weekend, which will probably involve trying to do one of these Wick theorem calculations. See, with guidance, of course, because it is a lot of work. Any questions? Yeah.
Is there a reason you didn't write an I epsilon on the denominator that time?
Oh, No, well,
Just-
you can. But
okay.
Maybe we should always do it reflexively, but it basically won't. It won't be something concerning unless you really allow. Basically, there are not going to be any momentum combinations where this will diverge. So it's only going to be for S-channel types of things.
Okay.
So we'll have that.
Okay.
We'll have to worry about the I epsilon description.
Sure.
But yeah, by default, we should always include it just in case.
Okay.
All right. Well, I'll see you guys next week. Have a good weekend.
Does that, when you do like a psi scattering off a sidebar and it exchanges the scalar, then do you not have an interchange of particles because?
Oh yeah, right.
So then it,
That's right.
okay.
Yeah. So there's no U. So then it's just T and S.
Okay.
Yeah,
So then
yeah.
you don't worry about the minus.
Well, then you don't even have actually.
Yeah,
can't
you don't
write
even
a
have
U-channel.
that.
Yeah,
Yeah.
you can't write a U channel because of that.
Okay. Yeah, that's right.
Does that make sense? Because
Yep.
then, yeah.
And if you do all this in a magnetic field, does it get like crazy complicated? Because then the energy depends on the spin, or
Oh yeah. I don't think. Yeah.
does it not?
No, thankfully we don't have to deal with that. So I
Okay.
mean,
Yeah.
that would break also this assumption of starting with free
Yeah.
field free theory eigenstates.
Right.
Yeah.
Okay.
But presumably you can do it, and it may not be that bad.
Yeah. Okay.
Just have a different eigenstate structure to worry about.
Yeah. Okay.
Yeah.
Okay.
There may be methods already developed to deal
Okay.
with that, but
I was just thinking when you were writing down the normalization has the energy in it, and it's only as a function of momentum. Then I thought if that's actually a
Yeah,
function
yeah,
of
that's
spin,
true.
then yeah,
Yeah.
could get kind of nightmare.
yes, that would be annoying. Then you have those two things coupled.
Yeah. Yeah.
At least in elementary particles, we don't have to worry about that very much.
Yeah. Okay. That's hard enough.